My name is Klaus Iglberger. I'm working at CD-adapco, now a Siemens business, and today I'm going to talk about the BLAS math library. So I know it's 9 o'clock in the morning and you have chosen a talk that has math in the title, and so I assume that you have real interest in this topic. So I highly appreciate you being here. I assume that you all have some familiarity with C++ math libraries, else you probably wouldn't be here, or you have interest in using such a library. So I'm a curious guy. Who of you is currently using a C++ math library in his code? Okay, this is 80% perhaps. I'm a little more curious even, who's using Boost U+ by any chance? Okay, the eigen library? Okay, most of you. By any chance, the BLAS library? Okay, not yet. So then I have to just do a good job to convince you. All right. So the primary idea, the essential idea of these math libraries is to give you some very, very convenient, intuitive interface to write your code and at the same time provide you the maximum performance that you can expect. So for instance, if you want just to write the CG algorithm, you should be able to take a textbook, copy the algorithm from the textbook directly in C++ code, and this should be it. It should run as efficiently as possible. At the same time, it is as readable as possible. So if you know the CG algorithm, if you do not, don't worry. If you know it, you can read it. It's very easy to maintain. This is kind of the best of both worlds. Maintainability and performance at the same time. And BLAS just happens to be one of these math libraries. So BLAS is an open source C++ math library under the BSD 3-class license. It is a math library for dense and sparse arithmetic. So there's dense and there's sparse vectors and matrices available. It is a header-only template library. So all you have to do is include a header, use the stuff, and the code that you need is generated on the fly. And it is based, as you might have guessed, on expression templates. To give you a little bit of sales information, BLAS is offering you high performance, both through the integration of BLAS kernels. So you can use a BLAS library, also a LAPACK library in the back, and it will just call into these libraries. Also, it is having a couple of manually tuned kernels, and it's alternating between these two alternatives depending on the situation. It is using vectorization, explicit vectorization, both by SSE, AVX 512. This is the AVX for Knight's Corner, Knight's Landing, so the new Xeon Phi architectures, Fuse Multiply Add, and Intel's SVML. It provides parallel execution of, or by OpenMP, C++ 11 threads and also Boost threads. So you can choose whatever you have available. It provides, hopefully, a very intuitive and easy API, so similar to domain-specific language. You just use it as you think it should be used, probably works. Provides unified arithmetic, I mentioned this already, dense and sparse vectors and matrices, and you can combine them. You have a sparse matrix and a dense matrix, you can multiply them, no problem. It is thoroughly tested, so currently there's over 6,000 executables for testing. This is not a number that is convincing, but it shows we put a lot of effort in testing this library, and we try to be very portable and provide high quality C++ source code. Okay. In 2012, the first version of BLAS was released. So this was about 4 years ago. In August 2016, so just 1 month back, we released the current version 3.0, which is written in C++ 11 and 14, so meaning you need 14, then you can use this version. If you need anything C++ 98 specific, then just use the older, the release one before, version 2.6. This is still providing C++ 98. Okay, this might be the thought that you have in your mind. Come on, another math library, because you might know there's actually quite a lot around. So I mentioned the Boost library, so Boost U+, the eigen library, the MTL, Armadillo. There's a bunch of them. Why just another math library? Please hold the thought. I will answer it, hopefully. However, I would like to put this question at the end, all right? So give me some time to explain why. First of all, I would like to explain a little bit about the benchmarks, because of course I'm going to show you benchmarks, and you should know how they work and what exactly is benchmarked here. So I use an Intel Haswell 10-core Xeon with 2.3 gigahertz. Haswell because this architecture supports fused multiply add. This is a very important quality of the processor. Turbo Boost is disabled, which means I stick to 2.3 gigahertz. It will not increase speed to 3 point whatever. And this is also important to have reliable deterministic performance results. I use both the GNU compiler in version 6.1 and the Clang 3.8 compiler to show you some differences. This is not a battle of compilers. I just want to highlight a couple of very important points. So even if one compiler seems to be better, this is not what I want to tell you. And this is how I compile, so just showing this with G++. I use AVX explicitly, fused multiply add, of course no debugging, and C++14 is required. This is all. All right? Then, this is one example of such a benchmark kernel. So for instance, a vector addition of two vectors. There is a loop that repeats these benchmarks, and every benchmark is running for at least 2 seconds. This makes sure that really everything is leveling out. All jitter of OS, etc. should average out. Samples are, so I collect samples in each of several runs. So there's really several runs, very important. And I collect several samples, as you see here. And also all cache problems are hot. The operation, whatever it is computed once before I start. Then, if possible, everything is already in the cache. And then I start the benchmarking. Okay? So the libraries that I do benchmark is, of course, BLAS 3.0. The release was in August 2016. Then the Eigen library that most of you use. I chose the beta 2 version for a very specific reason. So beta always sounds a little half finished, but only the beta version supports AVX and FMA. Else I would only have SSE. This would be a pretty unfair comparison. I have chosen the Armadillo library in version 7.3, released in June 2016, so also the most current version. Boost UBLAS, the most current version, so I use Boost in version 1.61, but the last update to UBLAS was in version 1.57, so November 2014. Since then, nobody has added or changed anything here. The good old Blitz++ library. A couple of you might remember, this was the first expression template-based math library. The last change was in March 2014, so quite a while back. GMM++ in version 5.0. Admittedly, by now they have 5.1 out, but unfortunately it was a little late for the benchmarks. So this was July 2015. MTL4 in the latest version, 4.0.9555. Latest change in May 2014. And as a comparison, this is not an expression template-based math library, of course, but as a performance comparison, Intel's MKL in version 14.0. Also, there's a new version, 15 is already out, but unfortunately I didn't have access to this. It shouldn't make much of a difference, though. Okay. Now, hopefully you know everything about the benchmarks. Let's start very slow. Yes, it's still morning. With BLAS level 1, meaning just vector operations. And for BLAS level 1, BLAS provides a couple of vector types. The first one is static vector. Static vector is a fixed size vector. So you give it a size at compile time. It will always be a, for instance, 3-dimensional vector. It will never change its size, and so the size is also available at compile time, can be used at compile time for certain optimizations. The opposite is dynamic vector. It uses dynamic memory, as the name suggests. You don't give it a size at compile time, but of course at runtime. You can resize this vector. It's very convenient for large vectors. Something in between is hybrid vector. Hybrid vector uses static memory at maximum n values, but you can still resize up to this size n. This is pretty convenient if you have some means to determine the maximum number, and it's hopefully a small number because you use static memory, but still you don't know exactly the size. So for instance, this might happen if you have 2 or 3-dimensional arithmetic. Yes, a question?
What is the parameter, the bool TF?
Okay, so the question was, what is the parameter bool TF? This is the transpose flag. I know, okay, it's a little cryptic. You can have a row vector or a column vector. BLAS makes a big distinguish pretty much between column vectors and row vectors. For instance, if you add 2 row vectors, the result is a row vector. You cannot add a column and a row vector. You can multiply them though. So if you multiply 2 row vectors, it's a row vector. If you multiply a row vector and a column vector, it's an outer product. If you multiply a row vector and a column vector, it's an inner product. There is also dot function and outer function if you don't like this particular syntax, but it's possible. So if I want, for instance, as I just showed you or explained to you, add 2 vectors, then this is how it looks like. You create vectors, 2 dynamic column vectors. I always use double. ABC, all with the size n, then I just add them. Very convenient, very easy. This is what you use if you use eigen too. So eigen does exactly the same thing. All right, now you're curious how this performs. Well, this is the performance graph for Clang 3.8. What you have to look out for if we want to see the BLAS results is the red curve. So you very nicely see the different cache sizes. So the performance goes up please note this is logarithmic scale. It goes up while it's still in level 1, then there's a performance drop. This is level 2 size, then a performance drop again, level 3, and last but not least, for very large vectors, you have to work from main memory. The first thing that is obvious, okay, for small vectors, there's a high jitter. But this is kind of the expected, it's very small vectors. BLAS is not running bad in level 1, so for some time it tops all the other libraries. There is not a big difference here in level 2, but very obviously in level 3 cache and from main memory, BLAS is about 20 to 25% faster than all the other libraries. I'll explain why. So one other thing that is strange, I don't know why, the MTL does not pretty well work with the Clang compiler. There's something going on. This is not what it usually performs. So this must be a problem of the combination of the MTL and the Clang compiler. If you use GCC instead, this problem is gone. And you see that the general picture is pretty similar, but BLAS still in level 1 dominates the performance. I'm pretty surprised actually that Boost U+ has such a high performance for very small vectors. This is a little surprising, but okay. I didn't invest this further. Again, in level 3 and in main memory, BLAS is about 20 to 25% faster. Question?
Flip back to the past slide.
Yes.
So you do better with Clang?
This is actually true, but as I said, I don't want to compare compilers. So the question was, I'm doing better with Clang 3.8 than with GCC. This is true. The maximum performance is a little better. But as I said, I don't want to compare compilers. The important point here is, whatever compiler you use, BLAS in level 1 will be the fastest library. All right. How many cores do we use at this point? This is an easy question. 1 core. How many cores do we have available? Perhaps you remember?
10.
We have 10 cores available. This seems to be pretty wasteful. 9 cores are idling while 1 core is computing a vector addition. Okay, let's just turn on parallelization, because today you will not get a 1-core CPU anymore. Everything is multi-core. Even my phone has several cores. So it's reasonable to assume that by using something like OpenMP, performance will improve. I will not use all 10 threads or cores though, but 4. The decision was made because I believe you do not have 10 cores available at home. It's a pretty expensive CPU, but 4 should be available everywhere. So I just use 4, why not? And I make sure that threads are pinned. This is actually something pretty important. So I make sure that the first 4 cores are used, none of the others. All right, this is what it looks like. There's just one library that actually benefits from parallelization, and it's BLAS. However, it does not benefit immediately. So for small and medium-sized vectors, parallelization is actually counterproductive. Performance would drop. Why? Because vector addition is not a lot to compute. It's just very fast. And the setup of threads, the distribution of work takes time too. So there is a certain additional overhead. But once the vectors are large enough, parallelization truly gives you benefit. There's a threshold where you can tune this in BLAS. So there's a question. I just use, so the question was, do I use OpenMP and the MTL? I'm sorry. I just use OpenMP in the command line. If this activates it in, okay. All right, then.
Has an extra flag for it.
Okay, so the MTL has an extra flag for it. Okay. Good to know. All right. However, what you see here is perhaps a little bit surprising. This performance is pretty low because we actually hit a memory wall at this point. We cannot go beyond it. This is why all libraries have exactly the same performance. It's not about computation, it's about the memory. But using several threads actually gives you a performance benefit. And the performance benefit is because you can, on modern architectures, only achieve high performance with several threads. So you can only go beyond this memory wall with several threads. And so this is why you actually gain performance for even for a vector addition, something as simple as that. But as I said, only from a certain point on, so for larger vectors. All right, now you might be interested what's going on in the behind the covers. This is the kernel that is computing. So a question.
How many memory bands has this machine?
Oh, I don't know. So the question is, how many memory bands does the machine have?
As well, 32 strings.
Yeah.
If you're asking how many hardware streams, how many streams can the hardware track? 32.
So 32 hardware threads to load. Okay.
I mean memory channels.
Memory.
Oh, memory channels. Out of
Has 4, but it depends how many you populate. So
Okay, so the answer would be 4 memory channels.
You can put into per CPU.
All right.
How many did populate?
All right, so this is the kernel that is computing the vector addition. What is happening here? So the first thing that BLAS is doing, it is actually using padding. Padding means I add a couple of extra elements at the end of a vector. This doesn't make a big difference or any difference at all for large vectors, but for small vectors it does. So as long as I'm still in the range, perhaps 100 elements, you might see this. No remainder loop is necessary. Then the kernel is based on iterators. That gives the compiler actually quite some opportunity for the additional optimizations. So with index-based access, I do not gain this performance. Then manual loop unrolling. Yes, Chandler would not be proud. Chandler has the opinion that this is something that should be done by the compiler. Yet you see that it depends on the compiler. Some compilers do this fine, Clang does apparently. Other compilers don't do it. Since I do it manually, I'm not depending on compiler optimization so much. You see this actually pays off. This here is something that is expression template specific. Load something that is happening on the right side. This is basically the SIMD vectorization. This is happening under the cover. So you have to believe me that this here executes SIMD operations in the according instruction set that you've chosen. For small vectors, everything is manual unrolled. For large vectors, this doesn't pay off anymore because we're memory bound. But what we can do instead is, instead of simple store operations, we can use non-temporal stores. Non-temporal stores mean I do not directly write back to cache, but I circumvent the cache, write directly back to main memory, which is pretty clever here because I don't need these values anymore. And by doing this, I actually free up a little bit of bandwidth. And this extra bandwidth that I gain actually makes up for these 20–25% in performance. Yeah? All right. What you do not see here is parallelization. There's nothing here that would indicate that this is actually running in parallel. No threading, no OpenMP pragma, nothing. Let's just have this as an interesting piece of information right now. I will go into much more detail later. Yeah? Just remember, kernels are not parallel, or do not contain parallel information. All right, now you might argue, well, but Fortran is of course faster, and so something like the MKL will probably run much more efficiently. So let's choose something that the MKL provides, a DAXB operation, just as a comparison. So DAXB is vector plus equal another vector times a scalar. This is something that is directly available in MKL, and so the orange graph now is Intel's MKL. And interestingly, for this particular operation, BLAS is even quite a bit more efficient than the MKL due to manual loop unrolling, vectorization, etc. But of course, the Clang compiler has quite a bit of additional part in this. There is no streaming going on here, no non-temporal store. So the performance in the end is exactly the same for all libraries. You cannot use streaming for this operation. This would be bad for performance because you still need the stuff. So the target is part of the operation. It's not just written to. GCC, very similar picture. But in this case, the MKL and BLAS are approximately the same, have approximately the same performance. There's one more library that actually has the same, approximately the same performance. This is GMM++. All right, parallel. At some point, again, it is worthwhile to use parallelization. The Intel MKL is, of course, parallel too. And so there's these two libraries that participate in the parallelization. BLAS a little faster, but in the end, the performance is exactly the same. But the manual optimization is good. Yes, question.
Does BLAS do any kind of automatic decision on when to start the parallelization?
So the question is, does BLAS have a decision when to make the parallelization? Yes, it does. There is a threshold that they can manually configure which decides at which point parallelization is considered. Below this threshold, no parallelization is used. Above the threshold, parallelization will kick in. Okay, question.
Maybe any tools, thread tools used to not constantly bring up threads between multiple operations?
So the question is, do I use any kind of thread pools? For OpenMP, this is part of the OpenMP system. If you use the C++11 threads instead, yes, then I use a thread pool. You do not have to create threads all over again. The disadvantage of the thread pool approach is that you have to take care of pinning the threads yourself. This is not part of C++11 yet, and also not part of BLAS yet, unfortunately. So as long as you pin the threads to a certain core, you should get approximately the same performance. Any other question?
Yeah, so how do you align your arrays, and do you do anything to try to mitigate cache aliasing conflicts?
Okay, the question is, how do I align the memory? So the memory is aligned by just properly allocating the memory, meaning there are special functions like POSIX memoline that you use to get aligned memory. This is essentially what is happening here in this case. It's a dynamic vector. I get dynamic memory from these functions.
But do you just align everything to some power of 2, or just...
Whatever is required in SSE, you need everything to be 16-byte aligned, in AVX it's 32-byte aligned, in AVX 1264, and so on. So I take care of aligning properly. All right. So BLAS level 1, check, works well. BLAS level 2, this means that we also have some matrices. And quite for symmetry reasons, there's a static matrix. You pass it a number of rows and a number of columns at compile time, and this will be the size of this matrix until its end. The dynamic matrix doesn't take compile time arguments, but of course runtime arguments. You can resize the dynamic matrix as you want. The memory will be preserved. So there will not be a reallocation if you resize, as long as you stay within the size you've already acquired, so it has a capacity. Hybrid matrix, again, is something in between, uses static memory, but you can resize it up to the given size. So the rows, the number of rows is limited by m, the number of columns is limited by n. Okay. The operation that I want to show is a matrix vector multiplication. I have, for instance, a dynamic matrix, column major matrix A, size n by n, and a dynamic vector of n elements, so 2 of them, A and B. And as you would expect, I just multiply the matrix and the vector, assign it to another vector. Very convenient. This is the performance that you get. So the orange line is Intel's MKL. The purple line is the eigenlibrary. The blue line is the MTL. With Clang 3.8, you see for small in-cache matrix vector multiplications, BLAS has approximately a factor of 2 performance advantage. There's a slight advantage in level 3 cache. There's no real difference here anymore when you are in the main memory. But BLAS is always at least as good as the MKL, which, as I said, is kind of the comparison. Not too bad. The picture doesn't change much with the GNU compiler. Again, BLAS is by far the fastest library in cache. It is obviously faster in second level and third level cache too. Again, the performance is of all libraries is the same from memory, because the operation, after all, is also memory bound. All right. If you use parallelization for that, question.
Dense or column major dense?
Sorry.
Is it dense or sparse row or column major?
So the question was, is it a dense or sparse column major? It is a dense matrix. I use a dynamic matrix. So it is the dense matrix vector multiplication, column major matrix. All right. Parallelization. It takes off, as I said, when a threshold is crossed. But as you see, it is actually working quite nicely. For some time, actually, you gain an additional benefit due to the fact that if you parallelize this, give it to 4 threads, then the parts that you give to certain cores are small again. So you can again benefit from this high performance that you have for small vectors. This carries on for quite a while, but again, in the end, the performance of basically all libraries that do parallelization is the same again. There's one more library here, that the Armadillo library. This library also calls the MKL internally. And so the performance is virtually identical to the MKL. Okay. Why is it so efficient, the BLAS library for small and large matrices? The reason is that we distinguish between small and large matrix vector multiplications. Small means I'm below a certain threshold, also something that you can configure, and I don't care about memory optimization, cache optimization. I know it is in cache. And so I can exploit a couple of extra information. This is why it runs pretty efficiently. As soon as I cross a certain threshold, I call a large kernel. This can be, if you want to, the MKL. It can also be the BLAS own kernel. So what you've seen the performance is actually BLAS's own kernel. There's not a big difference between the MKL. All right, let's move to the maximum level, BLAS level 3, which means we have only matrices. And of course, this is about the matrix multiplication. So if I have, now I have 3 matrices, a dynamic matrix, double column major, 3 column major matrices, all n by n. I just multiply them. This is matrix multiplication. Admittedly, this graph is a little boring because there's only 2 possible alternatives that this is working. Either the codes call the MKL, which is quite a reasonable thing to do, or alternatively, they call their own kernels, and there's only one library that uses own kernels. This is the eigenlibrary. There's one specialty here for small matrix multiplications. Again, BLAS is faster because we have a specifically tuned kernel for small matrix multiplications. Again, We distinguish between small and large. You can configure what small means. As long as we're in the small range, the small kernel is used, and this gives you a performance benefit. At some point, I simply switch from the BLAS kernels to the MKL, and you see then the performance is identical. The picture doesn't change much if I use GCC instead of Clang, simply because the MKL is called, so the MKL call is always the same. This is pretty compiler independent. It changes a little bit for these manual kernels of the BLAS library. All right, using parallelization, this is what it looks like. At some point, parallelization kicks off, in the case of BLAS a little earlier than in case of the MKL. In the end, however, again, the performance is the same. But what you see is you really get what you would expect in this case, 4 times performance improvement. In case of the matrix multiplication, this is possible because it is really arithmetically bound. That's a question.
So all of these, for the BLAS level 3 benchmarks, you're calling the Intel MKL kernels from BLAS?
So the question is BLAS always calling the MKL kernels? From a certain point on, yes. For large matrices, yes. BLAS does not have a kernel that can match the performance of the MKL. There's no chance that we can ever match this performance. For small matrices, however, we can actually surpass the performance because we can draw so much more information so much more performance from the information that is in cache. And so we deal with this differently. So at this point here, we call at this point here, the parallelization starts. But at this point here, definitely we call into the MKL, and the parallel version of the MKL. All right. I told you we have also compressed matrices, meaning sparse matrices. Yeah. There is currently one sparse matrix type in place called compressed matrix. You pass it a type, you pass it whether it's row or column major, and you can use this matrix type and combine it with any other matrix type. So for instance, also with dense matrices. So let's, for instance, see what happens if I have a compressed matrix A and a dynamic matrix B and C. So I multiply a sparse matrix with a dense matrix, sparse times dense, and assign the result to a dense matrix because the result is expected to be dense. This is what the performance looks like. There's so at some point a performance benefit of about a factor of 2, but overall, BLAS never is slower than any other library. So you can count on the fact that it will be faster. Let's play a little game, shall we? I have 4 libraries here, but you only see 3. There's 5 libraries here, but you only see 4 graphs. Where's the 5th one? Okay, you might have spotted the green glow of the x-axis. This is actually boost U+. U+ comes with an amazing 0.0 megaflops for this benchmark. So 0.0 is something, which is not what you would expect. So promise me, if you ever happen to come across a sparse matrix multiplication or sparse dense matrix multiplication of boost U+, replace it with something else. It's definitely not what you like. The question?
MTL doesn't do a sparse dense matrix multiplication. It converts the sparse into a dense matrix because I thought nobody uses this.
Okay.
Do you do a real application that uses dense sparse matrix?
So it was a comment that the MTL does not have an intrinsic kernel for sparse times dense matrix. It converts the sparse matrix to dense matrix, correct? So this is why at some point performance is simply was too slow, so I stopped it. The same, of course, happened with boost U+. So the question was, do I know an application of this?
I think sparse dense operations come up in Cholesky factorization. We can talk about it.
Okay, and one
You should keep this sparse.
one proposed application is Cholesky, right?
Yeah.
Okay, but okay, I don't know either. All right. What you can do now, just as an experiment, is, okay, I forgot threads. If you use threads, This is an operation that is also parallelized. Kind of everything in BLAS is running parallel. And of course, you get a significant performance boost from that. Again, it only kicks off after a certain threshold, but after that, you can count on the fact that you get approximately a factor of 4 performance improvement. Okay, that's it. Let's do an experiment. I have a compressed matrix which is color major now. Okay, question, sorry.
Compressed matrix, is this some standard representation or is it your representation?
Okay, the question is, does the compressed matrix have a standard representation or is it something special, something homebrew? It is something in between. It is not a classical CRS or CCS format. It is something that allows you to fill it very efficiently. So it allows gaps. This is also why you're not allowed to traverse all elements, but only row or column wise, depending on whether it's a row or column major matrix. So it's kind of special. There is plans for now to also add the traditional formats. But the best thing you probably can do is first set up with a compressed matrix and then converge to the traditional formats. Yeah. Yes, question.
So the sparse benchmark, I'm not seeing armadillo there. Armadillo, from what I remember, they have a nice sparse matrix class.
They have sparse matrices. Some combinations, though, do not work. I don't remember exactly why this particular benchmark does not apply. All right. So now I have a color major compressed matrix and a row major dense matrix. This is kind of the worst case that I have. Color major sparse and row major dense on the right. Okay, so how do the libraries perform in this particular case? You see, all libraries that provide this have problems, perhaps because there's a conversion to a dense matrix. I don't know, so the performance is pretty similar. Perhaps the approach is equal. BLAS, however, performs much, much better. Surprisingly good. What's the reason behind this? Okay. And also, of course, this is running parallel too. And again, you gain approximately a factor of 4 in performance, which gives you a huge performance benefit. What is happening here? So this is the kernel for this particular operation. There's not much. There's a simple trick. If you, again, beyond a certain threshold, yeah, then I realized that it would be very bad for performance that to compute it just like it is. So I create a temporary. I create a temporary for the sparse matrix. I turn it from a column major to row major. Then I have a row major sparse times a row major column, row major sparse matrix times a row major dense matrix. And this actually works pretty well. This is why the performance does not drop so rapidly. All right. This is the classical operations, BLAS level 1, 2, and 3. You got an impression, okay, this is working well. However, one of the benefits of these libraries is that you can actually create complex expressions. Complex expressions mean you can concatenate things. Now I've chosen one example that is, pretty interesting. I have a dynamic matrix A and a dynamic matrix B, column major, both of them. And I have 3 vectors, A, B, and C. I combine them in this fashion. A times B times A plus B. All right. Usually this is evaluated in following order, left to right. Matrix times matrix, the result is a matrix again. This matrix is then used to multiplied with the vector addition. This is a matrix vector multiplication. However, much more beneficial for performance would be if I would evaluate it from right to left. First evaluate the vector addition. Create a temporary, whatever is necessary. Then compute a matrix vector multiplication with B. The result is a vector. And so then I can compute a second matrix vector multiplication, A times this temporary vector. Yes, of course, this is much more efficient simply because I've reduced the order of my computation from order 3 to order 2. Okay, second, I told you about these temporaries. How do these libraries actually evaluate this expression? Do they really create temporaries? Do they allow this expression at all? In case of BLAS, you just write it like this and can hope for the best. Other libraries approach this problem a little differently. So for instance, BoostU+ does not allow you to multiply a matrix product with anything else. So what you have to do, simply because else it doesn't compile, is you have to create a manual temporary. So the first thing you do is you compute b times a plus b, and the temporary result is then multiplied with a. All right. GM++ does also not allow this combination. In this case, you even have to explicitly add the two vectors first into the second temporary in order to be able to compile it. So you add a and b, you mult b with this temporary vector, and then the resulting temporary vector is used and multiplied with a. A similar approach is taken by the MTL, yeah? Which is good, which is absolutely reasonable. Armadillo allows you to write this expression directly. A times b times a plus b. As does eigen. It's a little different, so you should specify the no alias here, but else it looks pretty much alike. All right, this is what the performance is of these libraries. Again, BLAS, due to the strong matrix vector multiplication, performs pretty well. In the end, most libraries come up with a approximately similar result. What is not working so well, again, is BoostU+, and pretty surprisingly, the eigen library. Eigen does actually not recognize the fact that you should evaluate it in different order, yet the syntax allows it to write this expression, which is dangerous. This is something that actually shouldn't work if it is not evaluated in the right form, because probably there's a lot of people out there that would write exactly this expression and would be surprised by the fact that it's not running efficiently at all. Hopefully they benchmark first and realize it's running pretty slow. Of course, we can repair this defect pretty easily. We can just create the according temporaries. Yeah, we can compute the vector addition first, the first matrix vector multiplication, then the second matrix vector multiplication. Okay, a times temp b. And then, of course, the performance is what it's supposed to be. And eigen has, again, the same performance in the in case of memory, main memory computation for large matrices. All right. This can be parallelized too. Again, the BLAS library has a pretty significant performance advantage for some time. In the end, however, it's approximately the same performance. It's a little worse than the MKL. So both the other libraries call the MKL. It performs a little better, admittedly. So what is happening behind the covers in the BLAS library? Why can you write this expression? Because BLAS actually from the very beginning implemented restructuring expressions. So usually expression templates are just built and then you evaluate the tree. BLAS is actually able to restructure the tree, so to re-evaluate expressions, shift expressions to whatever is necessary. This is the kernel to turn a matrix-matrix multiplication into something else. If you have a matrix-matrix multiplication, so this dense matrix happens to be some form of matrix multiplication, and this is multiplied with a vector, dense vector, then what is done here is I just set parentheses explicitly. Please evaluate the right part first and then multiply with the left-hand side matrix. This is only possible if you have built the expression template library such that you can actually rearrange this. This is not always possible. All right. Performance is great. Now you might be interested in a couple of more features, what is available. So there's views also. We have a couple of views, subvector, submatrix, row and column. Subvector, of course, being something that you can apply to any kind of vector. Submatrix, row and column being something that you apply to matrices. So, for instance, what you can do is you can assign a subvector of some vector with its dense or sparse to a row of matrix A. So assign to the second row of A the subvector from X, or a subvector of X, starting at index 5 with a length of 8. Pretty convenient. You can also assign, for instance, to the row of a submatrix a certain elements. So you can be pretty specific. Please assign to these elements these values. Or alternatively, you can, of course, it's possible. You can assign a subvector of Y a subvector of a matrix vector multiplication, for instance. Well, this seems to be a feature that is not particularly important. Yet this is, believe me or not, the basis for the parallelization in BLAS. In BLAS, you can apply subvectors, submatrices, all kinds of views to any kind of expression. And this actually enables quite some interesting effects. So, for instance, this particular expression would mean, please assign to the subvector of the left-hand side vector from index 2 with a size of 4, something in the right, which is exactly this block. This is, if you take a close look at it, exactly the same as assigning a submatrix of A times the vector x. If you have such a mechanism in play, then actually you can just subvector, submatrix anything. So you get me a vector, I can create a subvector from this. You give me a matrix, I can create any kind of submatrix on this. And this is what is happening. This is how the parallelization is built. This is the parallelization kernel. So now you see actually a pragma, an OpenP pragma. Okay, forget about all the other stuff. The important part is down here. This line here. Please create a target. This is an aligned subvector of the left-hand side operand. And please create, or please assign to this a subvector of the right-hand side expression, whatever this is. Can be anything. I don't care. So all I have to do in order to parallelize all kernels is to write this kind of wrapper, apply subvector to what, or submatrix for matrices, to whatever right-hand side expression I have. It will be evaluated accordingly. And then everything can run in parallel. So in BLAS, not the kernels are parallel. The architecture is made parallel aware. Yeah? So there's just 3 or 4 files that have an OpenP pragma, whereas we have about 200 kernels. All right, performance, great. You've seen that with views, we achieve the parallelization. Now allow me to cover a couple of flexibility features that might come in handy. Because very often users of these libraries have special circumstances, and I cannot use it because of this special treatment of my code, so this special property. So let me start with custom vectors and matrices. There's 2 classes, 2 dense vector, a dense vector and an additional dense matrix that are called custom vector and custom matrix. These 2 classes are supposed to be used whenever you have something special going on and you cannot use the native data structures of the BLAS library. So let me give you an example. You have some kind of special memory, something that cannot be allocated by the library itself, something that is, well, special to you, wherever it comes from. Still, you want to be able to use the kernels of the library. What do? You just create a custom vector and pass it this kind of special memory. You give it, of course, also the information how many elements are making the vector. And additionally, you have to pass a couple of additional information. So is it aligned or not? If it's potentially unaligned, you just say so. It will be treated accordingly. Is it padded or not? Meaning, can I use some additional elements or not? In this case, I say unpadded. Then, of course, it might be necessary to run a remainder loop. Okay. If you have some other special memory, you can also, okay, let's say you have some aligned memory, then we can, for instance, create a custom matrix. We say, okay, this is aligned memory. I know for sure it is aligned. I also know that there's a couple of elements that you can use for extra padding. Yeah? You pass this memory to the matrix, for instance, give it the number of rows, the number of columns, how many elements can be used for padding. Additionally, you can also pass it a deleter. Please take care of the memory after you're done. Yeah? This might be important for various purposes. It is a custom deleter. You can pass anything that just cleans up this memory. Yeah? This custom vector, when it goes out of scope, will not touch the memory. This custom matrix, when it goes out of scope, will properly dispose the memory. Custom operations. Very often, people might not find the operation that they need in the library. So you might need a square root function. Okay, this is available, but just as an example, it might not for whatever purpose. And what you can do is you can actually run a for each. This gives you the ability to write custom element-wise or component-wise operations. A is some dense or sparse matrix, and the second argument is, for instance, a lambda. Please compute for every element of A the square root of the element. Assign this to B. This operation is not vectorized, but it is at least running in parallel. This is good. What if you want to vectorize this as well? Well, it's just a little more complicated. Instead of passing a lambda, which is just a one function, yeah, we have to create a functor. We just do exactly the same as the lambda does for us, so a little more boilerplate code. We write a function call operator, which returns a square root. We can now add a function called load. This load function is triggered whenever I can actually vectorize this expression. So it is passed a SIMD type. So SIMD double type is one of the player's intrinsic SIMD types for, you might guess, double precision elements. You are passed a double element. You can pass this, for instance, to the AVX square root function, and it is returning an according SIMD data type. Now it's running vectorized too. Now, of course, this is only working for AVX. So if AVX is not available, then this function is, this intrinsic function is not available, not so nice. And also this function is always parsed. So as soon as AVX is not available, there's a compilation error. This is a problem, or might be a problem. For this purpose, you can additionally add a SIMD-enabled function. The const expr function, so it must be a const expr function, returns a bool. And within this function, you return whether or not SIMD should be enabled or not. So it can be anything. In this case, I just need the information, is AVX available? Then return true, else return false. This function here should be a template. As soon as it's a template, there's no compilation error anymore if it is AVX, because it will be parsed, yes, but the availability of the intrinsic does not matter anymore. So as soon as AVX is enabled and this function returns true, the load function will be used, if you have double elements, of course. And suddenly this operation, this for each, is running in parallel and vectorized. So you have the ability to create custom operations that are vectorized and parallelized. Okay, last but not least, I would like to point out that there's also a feature to customize the error reporting mechanism. BLAS is supposed to be potentially used on very large machines, highly parallel machines, so machines with 1,000 cores, 1,000 CPUs even. In such highly parallel environments, throwing exceptions might not be a particularly good idea. Yeah, unfortunately. So the primary error reporting mechanism of the BLAS library is to throw an exception. If you add two vectors with different sizes, an exception is thrown because the size does not fit, for instance. If you want to change this behavior in order to enable this for very large machines, then all you have to do is to actually change this little macro. There's a macro called BLAS throw. It is passed an exception, and usually it just throws the exception. If you want it to behave differently, you just define this macro before you include any BLAS header. For instance, log some information and then gracefully abort with an MPI abort, for instance. A question.
But stuff would, so it's BLAS is not like conditionally no except based on this, right? So these
No.
exceptions would be disabled, but BLAS wouldn't suddenly become no except.
So the question is, if BLAS conditionally is no except for this kind of
Yeah.
customization. No, it's not. Yeah. All right. So, remember the question from the beginning? Come on, another math library. Well, okay. Of course, you can contribute to another math library, but you've seen a particular, quite a number of advantages of this new library, because I believe there is still room of improvement. First, BLAS really fulfills HPC requirements. So you can, to some extent at least, put your MKL to rest, which is not quite true. If you have dense matrix multiplications, then you should still have the MKL around, because BLAS calls these kernels. But you don't have to call them directly anymore. You can grab these calls with the BLAS library. BLAS is less dependent on compiler optimization than probably all other libraries. Yeah, if you have, you saw this in the beginning with the vector addition, if you just have a GCC compiler, you still get close to the maximum out of it. Also, BLAS is probably the only library that provides full support for multi-core CPUs. It doesn't matter what you try to compute, you can run this in parallel. Other libraries only provide this for mainly matrix-matrix multiplication. Yes, true, this benefits most, has the most benefit, but all operations somehow benefit from it eventually. And also, BLAS is smart enough for the average user. Other libraries can be misused to some extent. You might run into trouble because there's no optimization of certain expressions. BLAS tries to be truly smart. It tries to restructure expressions to an extent that you might not have realized that it's actually better to write it in a different way. So I believe BLAS's participation in the race benefits everyone. It's a good thing that we have an additional library. Just because of this presentation, if the Eigen guys view it, then on YouTube they will realize, oh, there's a bug in our library. They'll fix it. So even then you might get a benefit just because BLAS is around. Right, and with this, I'm happy to take a couple of more questions. So, please.
Do you have sparse decomposition?
So, the question is, do I have sparse decomposition? No, not yet. Question.
So did you run any of these benchmarks on MATLAB code? Because the expressions that BLAS or even Armadillo provides, it's very MATLAB-like, which is nice when you're transforming prototype code into production code. So that's why I'm just curious.
So the question is, did I at any point compare this to MATLAB? No, I did not.
Yeah. So if it's small matrices, it's very slow because there's interpretable, but if it's large, it's the same like NKL.
Yeah, that's what I heard.
Okay, so the comment was that for small matrices, the performance is like the MKL performance.
Yeah, for large.
For the large, sorry.
For small, you have the interpreter.
Yeah. Okay. Question?
Is there any ARM support? Will it run on Neon?
So the question is, do we have ARM support? There will be ARM support. Yes, we don't have it right now, unfortunately.
Just a quick one too. And when using a custom matrices, is there some easy way to find the preferred alignment from this library, or do you have to have some separate steps?
Okay, the question is, if I use such a custom matrix, is there an easy way to find the proper alignment? There's the according type traits in place that you can use too. So if you, for instance, use double, use align off, so not the standard align off, but alignment off, not the standard one, but the BLAS one, it will return the proper alignment for AVX, whatever you choose. This is probably the easiest way. Question?
To criticize you, you have wonderful numbers and wonderful performance benchmarks,
yeah.
But you started out with the conjugate gradient methods and you haven't shown any CG performance.
This is, so the comment is that the criticism, constructive criticism is, I did not show any performance numbers for ZG. This is true. Yeah.
You know why I'm asking. So something that MDL would do well, opposed to other column major operations.
Okay, so if you need a couple of more performance results from, so for instance, row major matrix times vector. Yeah, this is what, okay. Then just please take a look at the website. If you go to the website, to the very first site that you visit, there's a link to benchmarks. If you click on this, you will also get row major matrix times vector results. You will actually see that in this case, BLAS performs by a factor of 2 better than for in-cache than other libraries. This is about the same. Yes, question?
Is BLAS also faster to compile?
So the question is BLAS also faster to compile? Unfortunately, no. So there is, of course, a trade-off. So it does a lot more things with the expressions in other libraries. And this, of course, has a penalty in terms of compile time. It is probably slower than the competitors. However, it also provides more features in this regard. Right, the session is over officially. So I'm glad to take any questions afterwards. Please just come to me. All right, thank you for being here.